Good day, everyone. So, today you're going to learn about the ultraviolet visible spectroscopy. So, before we go through the UV spectrophotometer, so we're going to learn about the theory of electromagnetic radiation, which I have been explained in detail in chapter 1. Okay, but this is just for recall. Okay, and so from the theory of electromagnetic spectrum, okay, so you must know that there is absorption of energy and also emission of energy, and by the time the electromagnetic passing through the sample, it will form it will give a signal. Okay, it will give a signal, and basically the radiation of electromagnetic as a source of energy will be released as a photon. And by the time we want to talk about the energy, okay, so basically we are referring to the wave properties. So here you can see that the frequency of the wave equals to the velocity of light uh, divide wavelength. And so I hope that you already know that to calculate the photon energy, you must know the wavelength. So in order to know the wavelength, you must determine via experiment. Okay, so you need to do some experiment in order to calculate the photon energy emits from the radiation of the energy source. So here, as you can see that from this formula, E equals to hc or lambda. So you can see that h is the Planck constant. So this is the exact value, 6.63 times to 10 to the power of minus 34 joule second. And the c is the, as you know, that is the velocity of light, and the lambda is the wavelength. And what is actually happened to the electron is there are two processes. In this case, there are absorption process where the electron from the ground state will excite to the higher energy level, which is excited state. So by the time for during this process, it will absorb certain amount of energy from the outside, from the external source, okay, and then it will stay at the excited state. And when atom absorb radiation, so basically only electrons are excited. Okay, so basically they will the process of excitation only involve an electron. Okay, and from this process of absorption, electron transition, we can observe the line spectrum. So this line spectrum you can clearly see in the electromagnetic spectrum. Okay, and electronic transition. Okay, so what is electronic transition? Is the transition of an electron between two orbitals. Okay, so now let's look for the molecular absorption. So basically, when there is a molecular absorption, it means that molecules undergo three types of quantized transition when excited by ultraviolet, visible, and infrared radiation. So basically, the transition of electron will be quantized. Okay? Quantized means it will have a discrete of value uh, in during the excitation process. Okay, so as you can see that the energy will be decreased from the electronic transition. Next, go to vibrational transition, and the last one is rotational transition. So in here you can see that the less or The fewer energy required is a rotational transition. Okay, so now we go for the next part. When light passes through an object, the object will absorb certain of the wavelength. So it will leave the unabsorbed wavelength to be transmitted. Okay, so the process of absorb and transmitted, okay, it will depends on the molecule in your sample. Okay, and then from this transmitted of energy, it will or can be seen as a color, especially in the visible range. Okay, basically in the UV ultraviolet range, it is difficult to identify the color. Okay, okay. So in this is the table that we always refer, like starting from more or less 180 nanometer until 400 nanometer. Okay, so the color is UV, and basically it will not absorb any color, just only ultraviolet. And in the visible spectrum, you can see starting from 400 until 750, you can see the color changes. Okay, so you can see here from starting from violet, blue, blue green, green blue, green, yellow green, yellow orange, and also red. Okay, so basically, okay, for example, okay, if the emission um, uh, or if the chemical reaction occurred and it released a red color, it means that the sample absorbed a green blue color from the energy from the source of energy. Okay, so why is the red solution red? So in this case, because the object absorbs green component from the incoming white radiation and thus transmit a red component. Okay, so in this question, you can see that it transmit or emits the red component. Okay, that's why you can see it is red. Okay, so now we go in detail about the principle of ultraviolet visible spectroscopy. Okay, so basically the range of the wavelength for the absorption spectroscopy is starting from 160 nanometer to 780 nanometer, and this kind of instrument, the UV base, okay, UV base spectrophotometer, they use the conversion to absorbance, like absorbance equals to epsilon times B times C. So here you can see that it also equals to negative log transmittance. Okay, so this is the contra of between transmittance and absorbance. So in this case also, in this subtopic also, you will learn about the Beer's law, the instrumentation. And so when we talk about the range of the region of UVVs, okay, so basically it will absorb the range from about 10 to 300 nanometer, but most analytical useful region is from 200 to 380 nanometer. So this is called as the near UV region. Below 200 nanometer, the air absorbs substantially and the instruments are operated under vacuum condition. So basically, the UVs that we have in our lab now, that is not under vacuum condition. So basically, they are in between 200 until 300 nanometers. Okay, so here we also have the concept of electronic transition. So basically we implement the concept of electronic transition in each time of when you run your sample by using UV vis spectrophotometer. And then the next is as you can see, the visible region is the wavelength that can be seen by the human eyes. So basically, we can see a colorful of sample, okay, because the solution um, absorb and emits, okay, a variety of wavelength, okay, a variety of wavelength, and then so that's why we can see that the visible range is about between 380 nanometer until 780 nanometer. Okay, so this is the regions, okay, for ultraviolet, near ultraviolet, and also visible range. So that is the common range of wavelength. Okay, so ultraviolet between 200 nanometer until 400 nanometer, and visible is from 400 nanometer until 800 nanometer. Now we go for the transmittance and absorbance de Beer's law. Okay, so by the time we get the energy, the source of energy here, this is either UV lamp or a visible lamp, the tungsten lamp. So it will emit the energy, and then this energy, okay, as a P naught, the initial radiant power, and then it will uh, uh, go through the sample, and then it will give the P value. So P here is the final radiant power. So the formula for transmittance is equals to T equals to P over P naught. Okay. So basically, the signal will give you in percent transmittance. So percent transmittance is the P over P naught times 100%. Okay, so next the absorbance. Okay, so absorbance A equals to log P naught over P is equals to log 1 over T. So this is equals also to the epsilon times B and times C. Okay, so a plot of the amount of radiation absorbed by the sample as a function of the wavelength is called absorption spectrum. Okay, so basically this kind of process like absorption and emission, so it will depends on the wavelength. So the parameter here is the wavelength. Okay. And this is one example of the output from the UV-vis spectrophotometer. So you can see that the sample is called bromo blue. Okay, so the y-axis is absorbance and the x-axis is wavelength. So this wavelength is depending on your sample. Like bromo blue, it will have a lambda max or the maximum absorption at more or less here. Okay, so in between like 625, I guess. Okay. Okay, now we go for the exercise 2. What values of absorbance correspond to 100%, 10%, and 1% of transmittance? So you need to use the formula that I gave, and from definition of absorbance. So absorbance equals to negative log the transmittance. So here is 0. When you have a 100% transmittance, it means there are no absorbance at all occur. Then next is 10% of transmittance. So you use the formula A equals to negative log 0.1. So it will be equals to 1. Next, 1% of transmittance has A or absorbance equals to negative log 0.01. So you can see that the absorbance is a bit higher compared to the 10% of transmittance. So here, now we go for the Beer's law. So by the time we want to understand the Beer's law, we need to understand the absorption of radiant energy. So when there's a radiation, okay, at specific wavelength, so it will have a value of absorbance, but without the units. Okay, and it can be calculated by using A equals to epsilon times B times C. What is the symbol of this? So here you can see that A is represent the absorbance, B is the optical path distance. So basically B is the length of the your cuvettes. Okay, basically 1 centimeter. Okay, it doesn't give any effect. Okay, so we can say that the length of the cuvette is fixed. Okay, and next is the epsilon, the molar absorptivity. So this molar absorptivity depends on your sample. Okay, so basically they have the fixed value for different kinds of molecule. C is the concentration of your analyte. So for this exercise 3, you just simply use the formula of absorbance equals to epsilon times B times C. So here in this case, monochromatic light was passed through a 1 centimeter cell. So 1 centimeter cell here, okay, this is actually we call as a B value. And then cell containing 0.01 molar. So this is actually C value. Okay, and then of a given substance, the absorbance obtained was 0.245. So here the absorbance A value. Okay, so this is A, and next you need to calculate the molar absorptivity of the substance. So basically when you need to write the calculation, show the calculation, you can simply use the formula and then just fill in, replace the symbol with this value, and then at the end you can get the value of molar absorptivity. Okay, so this is the calibration curve. Okay, so basically the absorbance will directly proportional towards the concentration, and in this case we can see that the Beer's law must follow this order. It means that it must be absorbance directly proportional to the concentration of your analytes. So here next, this is the deviation. So basically most of the sample will not show or will not obey the Beer's law, okay, at certain time, because maybe due to the high concentration of the analytes. Okay, so it will affect that. And what we can say from here, there will be a positive and negative deviation. So basically this kind of deviation is a non-linear curve. Okay, so um, basically due to the fundamental limitation. Okay, fundamental limitation. Second is the chemical deviation, the analytes itself, and number 3 is the instrumental deviations. So this is the deviation that I mentioned just now. Okay, by the time you want to prepare the calibration curve, so there will be a positive deviation and also negative deviation. Okay, so this is a common problem, since at certain concentration value, uh, the ideal calibration curve will not follow the Beer's law. Okay, so this is a very common. Okay, so next, this is the limitation of Beer's law. So basically, Beer's law is only valid for a very low concentration of analyte. So at high concentration of analyte, it will have a problem to follow the Beer's law. So the individual particles of analyte no longer behave independently of one another. Okay, so this is the reason why at a high concentration, uh, uh, the Beer's law is not suggested to be followed. Okay, at high concentration. and the absorbance change and the value of absorbance or absorptivity change. Okay, so we can say that at high concentration of solid may result in a shift maximum absorption and may also change the value of the molar absorptivity epsilon. Okay, so the molar absorptivity depends on sample's refractive index. So basically, when there are too many analytes in the sample, so basically the epsilon will be changed. Okay, so the epsilon may change at high concentration, but at low concentration. Okay, and in this case, the refractive index will remain constant. Okay, so next, the chemical limitation of Beer's law. So basically, it occurs for absorbing species that are involved in equilibrium reaction. Okay, so this is an example. Okay, benzoic acid exists as a mixture of ionized and unionized form. So the lambda max, as you can see, the wavelength at maximum absorption. Okay, occurred at different value of lambda max. So you can see that benzoic acid at 273 nanometer and ionized benzoic acid is at 268 nanometer. So what we can say, in higher dilution of higher pH, more ionized benzoate is formed. Thus, absorbance at 273 nanometer decrease. On the other hand, at lower pH, benzoic acid remains in its unionized form, whereby the absorbance at 273 nanometer is optimized. So here you can see that the error might be occurred here due to the natural process of like benzoic acid hydrolysis, okay, to become uh, ionized. So this is the Beer's law, the derivation that we can see from the figure. So here you can see the absorbance versus concentration. So it will produce at more or less like this one is for the ionized form and this one is for the benzoic acid at neutral condition. Okay, so the next is the instrumental deviation. So Beer's law is only valid for monochromatic radiation, and the output from a continuous source like the deuterium lamp will always produce a specific bandwidth about plus or minus 5 nanometer. So there will be always some error. Okay, so in this case, like if you use like deuterium lamp, okay, so basically it will give you the range, okay, in between plus or minus 5 nanometer. So if you have 220 nanometer, so you can or it may imply about 215 until 225 nanometer. So this is the component of instrumentation. So for UV-based spectrophotometer, and then you can see that um, the from the source here, okay, it will go straight to the monochromator and it will have a like we call as a uh, what we call as BSN or something like that. Okay, and after that it will pass through your sample and then it will go through the detector and next to the meter. So this is the schematic diagram, which is very important. For UV spectrophotometer, we have two types of spectrophotometer. We have single beam, this one, and we also have double beam, this one. The only difference is how they set up to run the sample. Okay, like for this one, still the same source. It will emit the photon and then it will passing through the filter or monochromator, same. And here you can see there will be a shutter which is for the analysis to choose which light is supposed to be absorbed. Okay, and here you can see that this is the lens and this is for the double beam. So shutter, it will shut either for the reference cell or for the sample cell. Okay, so in the double beam actually we use uh, both reference cell. We run reference cell and sample cell at the same time. Okay, however, for the single beam we use first the reference cell, and after that we take the sample out, and then we put our sample cell in the same location of the reference cell, and then you take the reading. Okay, the p naught value. So in this case you can see that for the double beam you can see that the analysis is concurrent. It means that it passing through the sample cell and also the reference cell at the same time. So both will produce P naught and also P. So here you will have the photo detector, the same photo detector that for the double beam only it will have two photo detector in this case, and then it will go to the amplifier and then give you readout the reading. Okay, and here also it will pass into the it will go through the amplifier and then read out. Okay, so this is the thing that I mentioned just now, so just read it. Okay, so this is the advantage of double beam spectrophotometer. Okay, so basically when you have a double beam spectrophotometer, the sample and reference cell can be read simultaneously. Okay, so you doesn't have to wait for a long time. Okay, you just can simply run your sample in your reference cell. Okay, in this case reference cell is your blank solution. Okay, so number two is the composite the fluctuation and wavelength changes from the radiation source. So in this case it can actually reduce, okay, the fluctuation and wavelength changes. Okay, if you run your sample and reference cell at the same time. Next, allow continuous recording of spectra. Okay, so this is another good advantage that you can see that you can record, okay, the continuous of spectra if you use the double beam spectrophotometer. Okay, so now let's look for the component of the instrument. So first is the light source. Okay, the light source is like for visible region, we will use a tungsten filament lamp, and for the ultraviolet region, basically we will use the deuterium discharge lamp. Okay, and for the monochromator, okay, monochrome represent one color, so it will choose or it's kind of slit that can choose exact wavelength that can be used for your to absorb or to which is suitable for the analyte in your sample, okay, to detect your analyte in the sample. Okay, what is the function of monochromator? So it will restrict the wavelength that is to be used to a narrow band. So it will be means it means that it will be specific for a certain band of wavelength. And next, to enhance the selectivity and sensitivity of instrument. Okay. And next is narrow bandwidth, better adherence to Beer's law. So when you have a narrow bandwidth, so you can get exactly a sharp wavelength or sharp absorbance value. Not possible to produce radiation of a single wavelength. Okay. So in the component of monochromator, there is an entrance slit, okay, restrict unwanted radiation. Okay, so it's same like filter, we can call it as a filter. And then dispersion element separate the wavelength of the polychromatic radiation. Okay, because as we know that from one energy or one source of energy, from the source of light, they will produce the polychromatic, but we have now is the monochromatic. Okay, monochromatic. So in this case they will use the prism or reflection grating. Okay, and next is the exit slit. This is just for adjustable. Okay, so it will control the width of the band of the wavelength. Okay, so next this is just a very simple optical spectroscopy. So you can see that this is the entrance slit and it will passing through the lens. Okay, and it will go to the prism and then go again to the focusing lens, and it will go to the exit slit here. Okay. Okay, so this is the component for optical spectroscopy. So this is the source of energy, and then it will go to the entrance slit and go to the mirror, diffraction grating, and then go to the focusing mirror. And then here you can see that it will go to the small slit here, the exit slit. This is the grating monochromator. So sample container must be transparent, as you all know. Okay, must be transparent in the wavelength region being measured. So in this case, we have different kinds of sample container. For the UV region, we always use a cell or cuvette of quartz. Okay, and we also have for the visible region, we use a cell or cuvette of quartz or glass or plastic. So basically the size of cuvette is 1 centimeter times 1 centimeter. It is a square base, okay? And the volume commonly we use about 0.5 milliliter to 2 milliliter, depend on the sample size. Okay, now we go for the absorbing species, which is called chromophores. Okay, so why we need to learn about the absorbing species? Okay, because the absorbing groups or unsaturated organic groups in a molecule are called chromophores, but a molecule containing a chromophore is called chromogen. So uh, there must be one molecule that can absorb uh, the energy from the external. Okay, so here you can see the wavelength at which an organic molecule absorbs depends upon how tightly its electrons are bound. Okay, so shared electron in single bond of organic compounds are very firmly held. Absorption at wavelength in the vacuum, okay, not used for analytical purpose. Okay, so electron in double and triple bond are not as strongly held. Useful absorption peak in the UV region. Okay, so what can be analyzed? Okay, so basically chemical species that can absorb UV with radiation, of course. And the second one is chemical species that can form soluble complex with chromophoric reagents. Okay, so in this spectrometric analysis, there are two major approaches. One is to measure the radiant energy absorbed by the ion or molecule itself. So basically, this is most organic species and some inorganic species absorb ultraviolet or visible radiation and can be used for spectrophotometric analysis. Okay, so basically for the UVVs, we will use if you have a sample of your analyte is organic molecule, then it can be easily to be used. Okay, I mean if your analyte is organic molecule, then you can use UVVs. Okay, and the other approach is used on species that do not absorb a significant amount of light through the formation of complex formation. Okay, so basically um, this kind of analyte you need to add some additional chemical, okay, like chromophore, to make it absorb the light. Okay. So here the absorption in the UV-Vis region, chemical species that can absorb UV-Vis radiation. For example, organic chromophoric groups, unsaturated bond. Okay. Next, saturated organic. Okay, with heteroatoms such as oxygen, nitrogen, sulfur, or halogens. Okay, and next one is ions of the transition metals. Okay. Okay, so by the time we want to understand the electronic transition, so we need to understand what is pi, what is sigma, and non-bonding electron. Okay, so basically this is one example. Okay, CH and with the presence of oxygen here. So here this is C and H, the carbon and hydrogen will have what we call as a sigma bond here, and between carbon and oxygen there will be one sigma bond and one pi bond. So this is represent the double bond. Okay, and here we have this non-bonding electron. This is what we call as a lone pair. So for you to understand the sigma and pi orbitals, so this is the orbitals. Okay, the orbitals for the sigma orbitals. Okay, so you can see that the electron is delocalized in this area. Okay, and for B, this is pi orbital. The electron is here, and this is the orbital. Okay, that exists for the pi orbital. Okay, and this is C, the sigma star orbital. So here you can see that the shape is different compared to this sigma orbital. Okay, so this is very contra to the sigma orbital. And this is pi star. This is the, you see that the orbital is repulsed and different compared to the pi orbital. So basically, when we try to understand the sigma star or pi star and non-bonding electron, so basically it will show the some kinds of energy level. So here you can see that, like for this one, from the non-bonding electron, okay, it will produce the sigma star, the anti-bonding. Okay, so this is just a few example of the transition, electronic transition, and you can see that when you have the sigma bonding towards anti-bonding, so it shows a very large amount of energy is required. Okay, so basically, when you require a very large amount of energy, so it shows that it need to absorb a very high amount of energy. So it depends on your molecule. Okay, so basically this is the the table that shows the, like this one is the ethene. Okay, ethene does contain with the C double bond C, and the process excitation is from pi to pi star, and then the lambda max is at 171 nanometer, and the molar absorptivity is 15,000 in the solvent of hexane. So basically this will show something that relates to the excitation or electronic transition. So in this part, the chemical species that can form soluble complex with chromophoric reagents. Okay, for example, the thiocyanate ion for iron, cobalt, and molybdenum, diethyl lithiocarbamate for copper, diphenylthiocarbazone for lead, and 1,10 phenanthroline for iron. And this is the for the application part. Okay, so basically the application of UV spectroscopy in qualitative analysis is limited. Okay, because the absorption band tends to be broad and hence lacking in detail. Okay, and next, several absorbing compounds might absorb over similar wavelength range, and the absorption spectra might overlap considerably. Okay, so in this UV spectroscopy, basically the overlap of peak is commonly found in your output. So we need to do have the broad treatment of your sample before we can run using the ultraviolet visible spectroscopy. Okay. Okay, so for the quantitative analysis, as you all know that we need to prepare the calibration curve. So in order to prepare the calibration curve, you must have the standard curve method or external standard method. And the other one is standard additional method. So what is standard curve method or external standard method? So in this method, they use or carry out as follow. Ensure only the analyte in solution will absorb UV radiation strongly and not other substance in the sample. So you must make sure that in your solution of the standard solution must consist of only your analyte. Okay. Second, select the measurement wavelength. So you should know what is the lambda max for your analyte and try to run it just to check either the lambda max suggested, okay, is correct. Okay, you can just have a scan of your solution to determine the lambda max. Next is select an appropriate range of standard solution. So in order for you to run your sample, you must know what is the range of standard solution. Okay, so basically you need to know that what is the common concentration of your analyte. Then you can exactly prepare the series of standard solution that you need. Okay, so prepare standard solution. Next is prepare standard solutions and prepare your sample. And then take absorbance reading of standard solution. Okay, so after that you plot the absorbance versus concentration of your standard solution. Then you take the absorbance of sample and read off from a calibration graph. Okay, so absorbance of unknown solution must be within linear line. If it's outside range, dilution must be carried out. Okay, so maybe due to the or very concentrated solution, so you need to dilute your sample. Okay, so this is the calibration curve, okay, of absorbance versus the concentration of your analyte. So you can simply get your reading of concentration by reading the absorbance, okay, value of your sample, and then simply drag here and then go here, and then you can simply determine your sample your analyte concentration in the sample. So ideally calibration standards should be similar to the composition of the sample of various other components. So this is what we call as a matrix effect or interference. So we try very hard to remove the interference. Okay. So here the testing of phosphate content in cola sample. So you can see that this is phosphate, phosphate ion plus with certain reagent, and then it will produce a yellow color complex. So the cola color itself will impart a darker color as compared to the standard solution. This background color from the sample causes matrix or background interference. Okay, so there will be a matrix interference here. Okay, thus it actually gives a higher absorbance reading. Okay, how to overcome this matrix interference? Okay, so you need to use a sample blank. Okay, in the standard curve method. Okay, so what is sample blank? A sample that contains with solvent and sample, of course, same dilution as the sample solution, except the reagent for complex reaction. Okay, so in this case, you just simply prepare the dilution. Okay, just do the dilution. And then next is you can use the standard addition method. So what is standard addition method? Okay, when you want to use this method, you use when the solid or liquid matrix of sample is either unknown or so complex that an external standard cannot be used with confidence. Okay, so basically we will, if you cannot use the external standard method, so we will implement the standard addition method. Okay. Okay, so for this example, okay, so you can see the flow, okay, or the how they carry out the standard addition method. Okay, fixed amount of the unknown are added to each of the standard solution. So here, for example, this is your standard solution: 0 ml, 1 ml, 2 ml, and 3 ml. So your sample, you just simply add up with the fixed amount of volume, 1 milliliter, 1 milliliter for each of the standard solution. And then you take the reading and then simply plot the graph of calibration curve. Okay, and then you can simply the concentration of the unknown is obtained by extrapolation to zero absorbance. Okay. So in this case, this is the calibration curve of from the standard internal method. Okay, so here you can see just extrapolate your curve and then until here. Okay, so you can simply determine the concentration of your analyte. Okay, by ignoring the negative signal. Okay, so here you can see here is for one example to determine the copper in your sample, and then here you can see they try to extrapolate it. Okay, and then this is at in between 0.1 ppm until 0.2 ppm. Okay, so here the limitations. Okay, we have any method there we always a limit. Okay, so the assay response must be selective enough so that the response only comes from the analyte. If there is a matrix or any interference in your sample or in your solution, then there will be what we call as disturbance in your analysis. Then the concentration range of what the instrument response remains linear, tend to be quite narrow, factor of 10. So this is to avoid the error that comes from noise. Okay. And next, the benefit allow compensation for quite complex effect. Okay, so you can simply um, allow the compensation. Okay, for quite complex effect. Next is disadvantage. So a tedious set of standard solution are to be prepared for each sample. So you need to think, okay, um, uh, how, what about if you have a lots of sample? So this is the tedious things that you need to you need to think, okay, if you want to prepare a set of a standard solution, okay. Okay, so here we have the selection of wavelength. So in the selection of wavelength, absorbance measurements are usually made at the lambda max. Okay, so that's true. And this lambda max is actually determined experimentally by measuring the spectrum in absorbance versus wavelength in the selected solvent. So basically, what is the application for UV spectroscopy? So basically, especially in the environmental. Okay, so to detect phenol, to detect chlorine, fluoride in water and wastewater. For the pharmaceutical, we can use the antibiotics, hormone to detect vitamins and analgesics. Okay. Okay. Now, thank you very much. That's all for UV spectroscopy chapter, and I hope that you can understand a bit from this video. So thank you guys.